All right, hello. So I've given myself sort of a challenge. I want to write a piece of NES software using hardware that was available at the time, like, during its heyday. So here is kind of the setup I have put together, kind of cobbled together, if you ask me. But its main center focal point is the Apple II. It may look a bit haggard right now. I don't have the top on it right now. This is because I have an EPROM programmer card installed, and in order to quickly install and uninstall and burn EPROMs over and over, I've kind of got this this board set up on top just so I have easy air access to this card. And this card is kind of what culminated this entire project. I found this card and it immediately became apparent that I would be able to burn compiled machine code from the Apple onto EPROMs, pop them into an NES cartridge, and actually run them on the NES. So super happy that I came across this card on eBay. Let's see. So next I have the STAG PP42. It's my EPROM duplicator programmer. This is a bit of kit that was around during, I think, the late 70s, early 80s, something like that. So it's definitely date specific, era specific, and accurate. Obviously, floppies and stuff for the Apple II. I have some EPROMs here also that are correctly date coded for the NES as well. They're date coded 84. So I wanted to kind of be accurate there. Also, I'm not really going to use this much in this video series, but I do offhand have a 70s programmer's calculator, so for any decimal to hex conversion. So if I want to do a good old 255 convert to hex, it gives us FF. So I'm super thrilled to just have physical calculators most of the time, and this one does hex, so that makes me infinitely happy. You may see this kind of peeking out, and it may look a bit out of place. I don't use this at all to actually load from or save to. This is a floppy drive emulator. The only thing I use this to cheat for is the software. So this is the software for that EPROM programmer card. I can't source the original floppy drives. They're just so rare. The card is rare enough as it is. So I take disk files from online and I burn them to real floppies. So I am using the real floppy disk, but it's not the correct one. So forgive me there. I'm just trying to be as accurate as possible within my means, within reason. So yeah, that's the setup. I'll move over to the other camera. We'll get everything booted properly. We'll start from the start and we'll get programming. All right, so we've had kind of the quick overview of the setup here. Let's kind of get started. First thing I want to do is format a disk so we can kind of work from a single floppy the entire time. So I'm going to put the prodos utility in the floppy drive. I'm going to power everything up. This is going to load up the utilities. It allows us to copy files, delete files, format disks, copy disks completely over. So it's just that sort of utility. I'm going to wait for it to load into the computer. It does take quite a while. These computers are old and slow, so you gotta, give them their time. In the meantime, I'll show you this here. I've put a little sticker on the corner of this floppy. That's going to be the file, the floppy rather, that we're going to be working from. Okay, so it's asking me a question. It's asking me if I prefer the 80 column display or not. I'm going to hit no, just so the text is a little bit larger for y'all to be able to see a bit better. Okay, so that's loaded up. I can take this out of the floppy drive, set it aside. We'll put our floppy in here to be formatted. And it gives us all these options. We can copy, delete, yada yada. I'm just going to go to option 6, which is format a disk. I'm going to hit the 6 key. It's going to highlight that for us. I'm going to hit enter. And it's going to ask us where the slot and drive are located. I'm going to hit enter on that. The slot that my floppy controller's in is 7. So I'm going to hit 7, and it's drive number 1. I'll hit 1. Now I want to format this to DOS 3.3. The Merlin assembler, the files that it saves and reads and stuff, it's going to be DOS 3.3 format. So we want to be consistent with our application here. I'm going to select DOS 3.3 and hit enter. It's going to tell me to put the disk I wish to format in the drive, which we already did. It's then going to say, hey, are you really sure we're about to destroy this volume? It's going to get formatted, yes or no, and you want to click yes. You kind of heard that weird sound. I guess I get a bit of a backstory while this is formatting. Steve Wozniak, the designer of this computer and that floppy drive, was a wizard at reducing chip counts. So the board in that floppy drive doesn't have enough circuitry for them to have added a controller to detect the actual position of the head. So for it to start a format or start a read, it just slams the head at the beginning of the track just mindlessly. So it's a bit of a brute force way, and that's why that sound is sort of horrid and very obnoxious when you start formatting or reading disks. A little bit of history there. But awesome, it has formatted our disk. It is completely done. So we can set this to the side, and this will be the floppy we are going to be working from. So let's go ahead and open up Merlin. So this is the assembler. I have a copy of it. I don't have an original. So this is Merlin 2.4.7. This is the version with the full screen editor. Let's go ahead and pop this in. I'm just going to power cycle this and let that load up. Merlin takes a little while to load. There's a lot going on. It's a pretty robust program. I'm fairly happy with it. I wasn't expecting such a robust assembler for such an old machine. There's quite a few directives and stuff on there that are pretty useful for its time. And I guess we may get into some of that. But okay, so it's loaded up. I'm going to take the boot disk out of the drive. We'll put our blank disk in. And we will be off to the races, and we are ready to assemble. Let me cut the clip here, and I'll see you over in a new footage. Alright, so we are in Merlin. We're ready to write some actual assembly here. So just kind of a general overview. These are all the functions. We have catalog, load, save, read, write, all that kind of stuff. So I'm going to hit the E key for entering the editor to type in assembly. I'm going to hit the A key to enter the append mode of the editor. And this is going to give us the full screen editor. So I can tab around and write anywhere on screen and create our assembly code. So at the very top, I'm just going to use the Apple 8 command to give us a string of asterisks. Asterisk is the start of a remark or a comment. So anything after an asterisk, the assembler just ignores. And we can create a little banner here by using the Apple 8 and Apple 9 keys and just kind of, you know, tell ourselves what this section of code is all about. I'm just going to say main file. Alright, and close that off with another Apple 8, and we are ready. So just like any other assembler, you want to organize your code at 8000. So we're going to put an org statement there, just like normal. And let's just call this our main file because we're going to add a bunch of include statements and reference other files. So just like in another assembler, what you may be used to is .include quotation file.asm, that kind of thing. So this assembler doesn't use that exact syntax per se, but it's going to be the same idea. So let's see here. So it has a pseudo opcode called put. And it's going to put another file in line with this assembly, and then while it's assembling, it'll read that file, assemble it, and then continue on. So let's just say our first file is going to be called reset. And it's going to be equivalent here to .include reset.asm. Alright, so that's going to be equivalent. Obviously I need to spell reset correctly. I just noticed that error here. I'm just kind of fumbling around. Awesome, so that's right. And to put another file here in line, we would use another put statement, naturally. And this may be where all of our setup code lives. So this would be equivalent to include setup.asm or something of that nature. So you kind of get the idea. We're going to be creating separate files to reference, and this is just going to be like a make file. After all that, we're going to have forever loop. I'm just going to make this inline. I'm not going to make that a separate file because we're not going to do anything in the main loop. And we may want to have like our NMI. We're just going to return from that interrupt and not doing anything in that either. Obviously we may do that later on, but I want to try to start basically a hello world, and we're just going to set a palette color, turn on rendering, and see if we see that color on screen. So awesome. So I'm going to hit Apple Q to quit out of this, Q and enter to go to the main screen, and I'm going to hit the S key to save this source file. I'm going to call this make, because this is going to be our main make file. Cool, so that is there saved, ready for us to reference again. So now let's make these other two files here. So we have our reset code and our setup code. Let's go ahead and start our reset code. So I'm going to enter the editor. I'm going to type new to delete all the stuff that was in memory so far and just start a new file. Hit the append for the full screen editor. We're going to create a little cheeky banner up here as well. It's going to be reset code. I'll call this reset routine. I'm going to be a cheeky bugger and actually try to get my centering looking correctly, so sorry about this. Awesome, so that is reset code. Let's create a label for our vectors to reference. And first thing we do is we disable the interrupts. We clear decimal mode, because the NES doesn't use decimal mode. And then let's wait for some vblanks. I'm going to create a temporary label. So this is going to be called vblank. Let's first create a counter though. I'm going to load that into the X register. I'm going to do about twice. We'll bit test the 2002 register. The highest bit, bit number 7, is where we detect if we're in the non-maskable interrupt, if we're in vblank basically. And if that bit is a 1, then we're in vblank, and if it's a 0, then we're not in vblank. So we want to use those signed branches. So if that bit is a 1, a byte with the highest order bit 1 is technically a negative number. So we can use branch if plus back to our label and wait until it becomes a negative number to escape the branch. And the fact that we're doing this twice means we have to decrement our counter, and we branch if not equal back to that label as well. Cool. So that should be good. Let's set our stack as well. Let's go ahead, and we have to use the X register to set the stack. We know the value of the X register because we just escaped a branch if not equal, meaning the X register has to equal 0. Let's go ahead and decrement X. And this is setting X to FF because we knew it was 0 before. Decrementing it underflows it to F. And then we can set that to the stack. Set stack pointer. And now let's clean the RAM. Let's use X as a indexing register. So let's just increment that back to 0. And let's call this clean RAM. Okay, so let's load A with 0. We're going to store that in every single page of RAM. And we're going to index with X. We want to hit every 256 position of every single page in RAM. And the NES has 2 kilobytes of RAM. So when you do all the math and try to convert that to hex and work it all out, it turns out it's about 800 in hex. So we're going to do all these pages until we reach 700. So 0, 1, 2, 3, 4, all the way up to 7. Alright, just about done there. Indexing all those. Since we are using this X as an index and we want to hit every single spot on every single page, let's just increment X and branch if not equal back to clean RAM. The reason that we're not comparing it to anything else is because we want to overflow back to 0, ensuring that we've hit every single spot. Oh, and I need to spell RAM correctly. Cool. And then the last thing I want to do is just wait some more v-blanks. V-blank. We'll set that same counter, load X with 2. Bit test 2002, just like before. Branch if plus, just like before. Decrement X, branch if not equal. Cool, and that should be our reset routine done. We've, let me just recap. We've cleared our interrupts in decimal mode. We've waited some v-blanks. We've set our stack pointer. We've cleaned the entire RAM space to 0. We've waited a few more v-blanks. The reason we're concerned with v-blanks is because the PPU of the NES requires some v-blanks to be wasted before it's basically warmed up and ready for you to start accessing it. So awesome. We should quit out of this, hit the save button, call this reset, and save it to disk. One extra thing I want to do with this reset routine though is I need to hit the W key to write this as a text file. The reason there's 2 different files is because those put commands that we had in our make file earlier, it's expecting those to be in a text file format and not the original source format. And I know it's a little bit confusing, that's just the way this assembler goes, so we save it twice just so that those put statements can reference it correctly. Cool, so next let's create that setup file. Let's enter the editor, restart a new file by typing new, enter the full screen by hitting A and enter. Let's create our labels. This is going to be setup / initialization. Make sure my centering is correct. Okay, looks good to me. Awesome. So what do I want to do in setup? I want to tell the PPU that I want to access the video RAM and the palettes and all that kind of stuff, and I want to write the color pink to the screen. So the palettes live at 3F00, so I'm going to load a, actually let me just create a dummy label here, load pal for palettes. So I'm going to load A with 3F, and this is the high address of palette locations. I'm going to store that in 2006. Then I'm going to load 0, which is the low address of palettes. And I'm going to store that in the same exact register, 2006. This register does double duty. It basically is expecting the high address and then the low address. And there's a latch that can toggle to make sure that those happen in the correct order. So actually, let's reset that latch just to be safe here. We don't necessarily have to in this specific spot, just because I know the latch is set. But just as a matter of cause, let's reset the high-low latch. Cool. And the reason, again, just to recap, why we're telling it the address 3F00 is that's where palettes live. That's where the global palette for the background lives. So that's the one we want to alter. Awesome. Let's go ahead and load the value 14. And this is the palette color for pink. And let's go ahead and store that in 2007. And this is loading into the PPU. So 2007 is basically a port. So we've designated the address we want to affect, but we still just funnel data into the same register. 2007, 2007, 2007. So if I were to access 2007 a second time, oops, if I would spell it correctly as well, this would then write to 3F01. if I were to store to it again, this would then write to 3F02 and etc. and etc. It has an auto increment, and that's useful for when you're writing tiles to the screen, as well as palette colors and whatnot, but we're just gonna write this single palette color and call it a day. Actually, let's write all 4 palette colors here, just to kind of cover all of our bases. I want to make sure that these comments awesome. Okay, so store 2007, store 2007, and store 2007. So this is setting all 4 of the first palette's color to pink. Now, every time you do something with the PPU, the scroll registers normally get screwed up. So I'm just going to take care of that by loading 0 into the scroll registers, which is 2005. And again, there's going to be 2 of these writes on the same register because it's acting as double duty again. And that high-low latch from before is doing the same thing for these registers. So there's going to be the X scroll and the Y scroll, and the same register is responsible for both. We're just going to write 0 to both to reset them both. So that's taken care of there. The next thing I want to do is turn on the screen. Let me get my comments here real quick. Reset scroll. Let me do some better comments over here as well. So this is 3F00. We got 3F01, 3F02, 3F03. Perfect. Next, we want to turn on the screen. I'm also going to turn on NMIs. It's not strictly necessary because I'm not doing anything with the NMIs, but this bit of code is normally what I write anyway, so I'm going to keep it consistent with what I'm used to. This bit right here is turning on NMIs. Every other bit has some other function, not strictly necessary in this particular video, but this is the value I normally write. That other bit here is just making sure that the character page for sprites is designated correctly for what I'm used to, so I'm just going to leave it there. Okay, so let's rewrite this because I didn't write an LDA. And we're going to store that in the register 2000, which this turns on the NMI. Again, not strictly necessary in this example, but we're going to do it anyway. Then we're going to load this value. And this is enabling sprites, it's enabling the background, and it's enabling the background and sprites in specific regions of the screen. So we can have them to be visible. And we're going to do that in 2001, which is the register for those functions. Awesome. So this is enabling rendering. Perfect. I think this is done. Let me just double check. Reset high-low latch, 3F store, 00 store, pink 14, store in all the first 4 palette locations, reset the scroll, enable NMI, and turn on rendering. So that looks good. I'm going to quit out of here, hit save, Y. Oh, you know what I just did? I accidentally just barreled through that and overwrote our reset routine. Silly me. However, all is not lost. So let's ignore that just happened. I'm going to hit the save key once again. I'm going to call this setup. I'm going to hit enter. We're going to save it. I'm going to write a text file, same as last time, so the W key and Y to confirm. And funnily enough, this convoluted system with writing 2 different files is actually just what saved me, because I overrode our reset routine. I'll show you the problem. So if I hit load, reset, and enter, it's going to load. I'm going to hit the append mode. And look, it's all the code that we just finished. It's not all that reset code that we finished earlier. So we need to fix this. Let's quit. Let's actually go into the edit mode, start a new document so that everything's blanked. Let's quit. And I'm going to use the R key, which I rarely use, R, which is reading a text file. Remember, we've saved reset as a source file and as well as text. So let's just go ahead and read that reset text file. It's going to be our saving grace because you'll see that our reset code is back. Funnily enough, all is not lost even though I overwrote a file. So we kind of got away with a free one there. So let me quit out of here. I'm going to hit save, make sure it's reset this time, and hit the Y key to confirm. Cool. So let me load the makefile. I think we have everything we need. Yeah, reset setup, forever, return from interrupts. That should be everything. Okay, so let's open the makefile, and we're going to do a little bit more configuring so we can save everything automatically to disk. So organizing to 8,000, that's fine. We're putting these two in order in the way we need them. We have our forever loop. We have our NMI, which we do nothing with. And we want to assemble all of this code into another file. So let's use a directive called save. This is an automatic way to just save whatever it's assembled into a file and then continue assembling if we want to make separate files with separate code. So we're going to call this NES COL for NES color. And then I want to save my vectors, all my labels, to put in our vector locations. So I'm going to create a direct address for the NMI label. I'm going to designate a direct address for the reset label. And a direct address for the IRQ label, which we're just going to default it to 0. And we're going to save this into a separate file called vectors. So the only thing that NES color has is all of our code, and the only thing vectors has are the values for these labels, so we don't have to manually add those in the memory monitor. So this should be ready to save and ready to assemble. I'm going to quit out. I'm going to save that so it's saved onto disk in case we need it again. And let's enter the editor, hit ASM for assemble, and off to the races. It should assemble. Obviously it's slow going, these machines are slow, but this is the part I like to just sit back and watch. This is the most charming part about using these machines. You know, seeing the text scroll up, all the hex and the assembly and whatnot is just, it's what makes these machines worth coming back to, really. So this is complete. So it's given us our label locations, which we only got up to 65 in hex bytes long. So awesome. So that should be on disk. The next section, we want to actually write this to an EPROM. So what we want to do is let's load the EPROM software into disk. We'll just have that ready and waiting. And let's get some EPROMs. I'm going to cut the camera. We'll go over to my EPROMs and choose one out. Make sure one's blank. We'll pop it into the Apple and we'll get going. So let me turn this off and I'll see you over at the EPROM programmer. Alright, so we are at the point where we're working with EPROMs. So we're at the STAG. This is an EPROM programmer / duplicator that was around during the same era. I believe it's late 70s, early 80s era. So the correct kit for the job. I have a bunch of EPROMs here. I don't know what are on these. I think some are blank, but we're going to pop them into here and we're going to just check them out and see if they're blank or not. Just load these into each one. Luckily these zip sockets are super reliable, and even though that these are the original zip sockets, I haven't really had issues with specific pins not really reading because this bit of kit was made with quality components. So let's turn this guy on. It's going to initialize its own RAM upon startup just to make sure it's all cleared out. Awesome. Let's select the correct device. These are ST parts. So we're gonna go to the ST. We're gonna choose the 2C or 27C 2056, 256 rather. I can't speak today. You know what I mean. And we're going to make sure that these EPROMs are empty by hitting exit to make sure that it's selected and empty. So it's doing a bit of business behind the scenes. Obviously, it's performing the empty command, so it gives us empty on screen. And it's told us that these two chips have failed. These two red LEDs indicate the failed chips. So let's get these out of here, put these to the side. We'll erase those later on, but these remaining chips should be completely blank. I can run this just one more time as a sanity check, just to kind of prove that that's the case. The ones that remain green at the end of that empty check mean that they are cleared. So 4 parts pass. Awesome. So let's get these out of here. Obviously, these are ones that we can use to program our program onto. But I want to use this last chip here to create a character ROM. Obviously, there's 2 chips in an NES cartridge most of the time, at least for NROM. This right-hand one is going to be for programs, the program code, and this left one is going to be for your character set, all the graphical information. Our code doesn't really use graphics thus far, so I want to blank out our EPROM and pop that into that slot. So by default, EPROMs are filled with FF. I believe that's what RAM is already, RAM is currently reflecting FF. All the positions in RAM. So I want to load 0 into RAM. Let's go to set F0. It's the automatic command for that. Set F0. And it's going to load RAM with all zeros. Before you saw it was FF. That kind of matches with the default state of an EPROM. But now, if we list RAM, all that stuff is going to be a 0. Awesome. So let's go ahead and burn this guy by hitting program. Oh, let me exit here and hit program. And we are just basically blanking out this chip with zeros instead of Fs. Hopefully that doesn't take too long. This thing is a pretty old piece of kit, like I was mentioning, so it's not going to be instantaneous like you may be used to, and it's part of its charm. I keep saying these things are charming, and I'm going to stick by it because I love using this kind of kit for this sort of purpose. It kind of puts me in that headspace of, you know, what programmers used to be doing to create this stuff back in the day, and it shows me how hard it was to really push out some of these bangers of games that we're so used to. Obviously, it took studios and teams of people. So, you know, those amazing games like, you know, Mario, Contra, they had bits of kit that were of this era, and it wasn't like what we have today with like Messen emulators or like cross compilers and assemblers and whatnot that made it infinitely easy. Even the debuggers we have in our emulators, just they hold our hands. They didn't have any of that stuff back in the day. I'm sure they had hardware solutions to, you know, have sort of a similar scenario so they weren't completely blind, but it really puts things into perspective, you know, seeing what they may have had back in the day, and it's been a fun exercise thus far. I've been enjoying it. Cool, so good signs. We're at the verifying process. It is verifying all the bits, comparing the chip to the RAM, making sure it's correct, and now it has passed. Awesome. So this is our character ROM. This is basically just all zeros on an EPROM. Let's get this popped in here. Awesome. One EPROM down, another EPROM to go. We can go ahead and turn this guy off. It's done its duty. We can put it to sleep, and hopefully that fan will shut up and we can get back to coding on the Apple. Alright, so sorry about the huge jump in quality in terms of quality loss on the footage. I had to crank the ISO to kind of brighten up the image to kind of show you the card we're working with. I'm going to show a picture of this card on screen so you can get a better look at it. But this is basically our EPROM programmer card. Has a little ZIF socket here for putting EPROMs into. It has some toggle switches to set the configuration for the specific EPROM you're using. And then you basically you load in your EPROM into the zip socket, and it'll do your programming, reading, and all that kind of stuff. So I'm just gonna pop that into the ZIF. That will be ready to go, and we will get to our program, load it into RAM, and see if we can't burn this sucker. Alright, cool. So let's boot up the first disk of the EPROM programmer software. It's going to be a relatively quick boot, luckily enough. We'll get that out of the floppy drive. We will put our disk full of files back in. And let's start loading our machine code into the RAM of the Apple II. And once it's properly situated in RAM, we can use the burner software to pop it into the EPROM and burn it. So let's beload the NES program that we named NESCOL to the address location 1000. It's just a convenient open spot in RAM that we can store up to 32 kilobytes, luckily enough. So, and then next let's beload our vectors into the address location 8FFA. Now, obviously, the vectors of the system on the NES look for vectors at FFFA, and on EPROM they're located at 7FFA. But since we're loading all of our code 1000 hex above normal, we compensate for that by turning that 7 into an 8. So vectors should be in the correct spot. We can actually go into the machine code monitor and just double check that. So if we go to address location 1000, we look it up and disassemble it, we see that our setting the disabling interrupts and clearing the decimal mode, they're in the proper spot. They're at location 1000. We can continue on, and here's our jump location. So this has to be our NMI. You'll see that 8062 corresponds to what would be 8062 in this location. It's 1062 here. That's because we assembled it to location 1000. But our org statement makes sure that that label is correct for our NES program. We can look at vectors as well. Let's go to 8FFA. So 8FFA. And what do you know? We have 8065, just like we expected. Awesome, so that is correct. Let's go ahead and exit machine code monitor. Let's take our disk out. We've successfully loaded things into RAM. Let's get disk 2 for the programmer software. Pop it in the floppy drive. And we're going to run a program on disk called b.PROmGRAMER 2.3. Now it's going to load up and ask us what slot our EPROM or programmer card is located in our system, and I have that in slot 4, so I'm gonna hit 4. And then it's going to ask us how is that card configured. So we are burning 32 kilobyte EPROM, so that's option 7 for the 27256 series. So I'm going to hit 7, and we're in. So it has a couple different directives and options. We can read from the EPROM, we can burn an EPROM, we can compare it and verify it, and we can check that it's erased. I'm just going to double check. I'm going to hit the E key, and I'm going to hit enter, and it's going to check and verify that everything is erased. You may not be able to see the bottom right hand corner very well in the camera, but it's basically just running through all the address spaces, and that is just checking and verifying that they're all blank. And that chime means that we're good to go. So let's go ahead and hit the F key for the fast burn option and verify. We're going to tell this program that our code starts at 1000 by typing 1000. We're going to tell this program that our code ends at 8FFF, and then we're going to tell this program to assemble that code to the position 0000 on the EPROM. I'm going to go ahead and hit enter, and it's going to start assembling. Let me get my supplementary camera out here. Zoom in to the bottom right hand corner. This is chugging away. It's basically telling us every address that it's currently working on. So it's in the 1000 range right now. It's pretty slow going in the grand scheme of things, but it's pretty fast compared to the slow burn option that this software has. So it's going to chug away here for a little bit longer. It usually takes around 2 to 3 minutes to burn 32 kilobytes. It's not too bad in the grand scheme of things, like I've been saying, but it still is quite the wait if you're just trying to check a single change of your program. It's a bit cumbersome, so that's something I'm getting used to. But I'll let this chug away. We'll come back when it's verified, or at least close to being verified, and we'll pop it in the NES and see how it works. Alright, so it's doing its verifying thing. It's at the home stretch of the programming process. Awesome, and it's given us the positive chime, meaning that all is well. So let's go ahead and take this guy out of the card, pop this guy into the NES cartridge. Awesome, so let's take this over to the NES, and hopefully it gives us a pink screen. Now, I'm probably expecting an error or two. I'm going to be amazed if this works first try, but let's see if it works. And it is successful. Obviously I had to go with the Hello Kitty monitor to match the pink color that we decided to write to the screen, but yeah, it was a success. Obviously it's sort of a Hello World attempt and there's not much going on, but that just kind of gives you a glimpse into what it is like coding on such a amazing but limited machine. I hope you enjoyed. I'm definitely going to be making more videos expanding on this, and we'll be having more fun. Thanks for joining me. Bye.